To read a single file from a traditional hard drive, a mechanical arm sweeps across a magnetic platter spinning at thousands of revolutions per minute. The read head hovers just nanometers above the surface, physically searching for the exact microscopic sector where your data lives. That physical search introduces unavoidable delays. Rotational latency, seek times, and the constant risk of mechanical failure meant that modern computing speeds were permanently bottlenecked by how fast a motor could spin. This is a modern M2 solid-state drive. Data flows instantly from the PCIe connector, routes through the central controller, and is distributed directly into the NAND flash memory chips. By stripping away the motors and actuator arms, engineers replaced mechanical movement with silent silicon pathways. Storing data was no longer a physical task, it became an electrical one. Without a magnetic disk, an SSD needs a way to preserve data even when the power is turned off. The solution is the floating gate transistor, a microscopic vault built directly into the silicon to trap electrical charge. When the drive writes data, it applies a high voltage to the transistor. This creates a strong electric field, forcing electrons to quantum tunnel through an ultra-thin oxide barrier, locking them inside a central chamber. Once the voltage is removed, that barrier acts as a perfect insulator. The controller can later apply a tiny read voltage to detect the presence or absence of those trapped electrons, interpreting them as a binary 0 or 1. Every operating system, video game, and photograph you save is ultimately preserved as billions of these electrons held permanently in place inside microscopic cages. As software and media grew larger, consumers required terabytes of storage. Simply manufacturing larger silicon chips would have made SSDs prohibitively expensive for the average user, forcing engineers to find a way to pack more data into the exact same physical space. Instead of storing 1 bit per cell, they divided the cell's internal voltage capacity. A single-level cell has 2 distinct states. By splitting those energy levels into 4, then 8, and finally 16 distinct charge levels, a single transistor can hold 4 bits of data at once. This density creates a delicate balancing act. With 16 levels crammed into the same microscopic cell, the voltage windows become incredibly narrow. The slightest loss of charge makes it difficult for the drive to determine which exact data state is stored. Packing multiple bits into every cell solved the capacity problem, but it made the memory inherently fragile. To keep this dense architecture from collapsing, the SSD requires an intelligent system to manage the cells. That system is the SSD controller. It acts as a dedicated processor, operating an algorithmic command center to keep the drive functioning and your data intact. The controller's primary threat is physical wear. Every time high voltage forces electrons through a cell's protective oxide layer to erase and rewrite data, the insulation degrades. Over thousands of cycles, the cell will permanently fail. To prevent any single area from dying prematurely, the controller uses dynamic wear leveling. When you repeatedly save a file, the controller intercepts the data and redirects it to fresh, untouched blocks, spreading the stress evenly across the storage grid. It goes even further with static wear leveling. The controller quietly relocates dormant data, like your operating system files, into heavily worn blocks. This frees up the healthy memory for new, intense write cycles. Without this continuous internal shuffling, a heavily used section of the drive would burn out entirely in a matter of months. The algorithms actively extend the hardware's physical lifespan. Managing that space is complicated by a specific quirk of flash memory. You cannot directly overwrite old data. The SSD must erase an entire block of pages simultaneously before any new data can be written there. When the drive is idle, it performs garbage collection. The controller inspects fragmented blocks, copies the still valid data to a fresh location, and hits the old block with a high voltage pulse, wiping it completely clean for future use. Even with clean blocks, the drive still contends with microscopic imperfections in the silicon. Over time, trapped electrons slowly leak out of their cells, eventually altering the voltage enough to flip a binary 1 to a 0. To counter this, the controller generates error correction code, or ECC, alongside every file. This mathematical safety net continuously scans the memory blocks, identifying corrupted bits and instantly reconstructing the missing data using parity algorithms. Inside the drive, a constant war is waged against physics, wear, and entropy. Because the controller handles these maintenance operations flawlessly in the background, you experience a drive that simply works. This maintenance system requires physical space to operate. When you fill a solid-state drive past 90, instead of dropping a new file directly into an empty space, the controller is forced to move, erase, and rewrite existing data across multiple fragmented blocks simultaneously, just to make room. As this internal gridlock builds, the drive quickly exhausts its high-speed cache. The controller must write incoming files directly to the dense, slower memory layers, and your transfer speeds plummet. Leaving 10 to 20% of your solid-state drive completely empty provides the physical workspace the controller requires. That free space guarantees the survival algorithms have room to execute. As we push silicon structures to the atomic scale, engineers are nearing the absolute physical limits of how tightly we can trap electrons. To scale further, experimental architectures are moving away from traditional transistors. Researchers are successfully encoding digital data directly into the molecular structure of synthetic DNA, storing massive archives inside microscopic biological strands. Data storage has steadily condensed over decades. We moved from heavy magnetic platters to perfectly controlled electrons in solid silicon, and are now looking towards quantum states and phase change materials. Whether preserving a family photograph, the global financial system, or decades of scientific research, everything we create digitally relies entirely on our ability to engineer the invisible architecture of microscopic particles.